All right, for the next set of questions, we're going to start with the circuit. The battery in the diagram above is charged by a generator G. The generator has a terminal voltage of 120 volts when the charging current is 10 amps. The battery has an EMF of 100 volts and an internal resistance of 1 ohm. In order to charge the battery at 10 amps charging current, the resistance R should be set to. So this one is going to use Kirchhoff's law. No, thank you. There we go. It's going to use Kirchhoff's law, which states that the sum of the voltages across a circuit need to be 0. So for this, we have the voltage of the generator, voltage of the battery, and then the voltage across the resistor, and that should all be 0. Now if I take that, we got to expand out the resistor voltage, which we can use V equals IR, and we can plug that in. So I have IR, but the resistor has, or there's an internal resistance of 1, so we're going to put that into series. So I have R plus 1 is equal to 0. Then essentially we just plug numbers in. I have 120 volts, 100 volts, 10 amps. R plus 1 is 0. 20 minus 10R minus 10 is 0. Do some math and magic. I have minus 10R, and that's going to be plus 10. Minus 20 is minus 10, so R is 1 ohm, which is answer C. All right, next question. Let's erase this. A charged particle is released from rest in a region where there is a constant electric field and a constant magnetic field. If the two fields are parallel to each other, the path of the particle is. So if I have a particle, V equals 0, and it's released, and I have an E field and a B field, what does the particle do? So we can use Lorentz force, F equals QE plus QV cross B. And from there, we can look at a couple things. If I have that the velocity is 0, that just gives me, it's going to bother me. There we go. That QE plus 0. So if I have a force that's just based on the electric field, we're given that the electric field is a constant value. So that will also be a constant, which then tells me it's going to go in a straight line, which is answer E. Okay, that one was not too bad. Let's move on to the next question. All right, next problem. A nickel target is bombarded with fast electrons. The minimum electron kinetic energy needed to produce X-rays in the K series is most nearly. So, little diagram never hurts. I have, we'll just say some energy levels, and then down here. So I have the N equals 2, N equals 1, and it's saying the minimum kinetic energy, so it would be a 2 to 1 for the minimum. Now, looking at this, we have Z equal to 28, and we have the equation is E equals the Rydberg energy, Z minus 1 squared 1 NF squared minus 1 N initial squared. So taking that, and basically you're going to plug in values. I have energy. We'll just keep that there and fill that in later. 28 minus 1 squared, 1 over 1 squared, minus 1 over 2 squared. E 13.6, 27 squared, 1 minus quarter. Just doing some rounding because it's asking for nearly. I can just take that up to 15. 27 squares, about 900. 1 minus a quarter is 3/4. Doing that, I have that's roughly 12 by 900, which is roughly 10,000. These are all electron volts. Looking there, our answer is D. All right, now for the next question. The hypothesis that an electron possesses spin is qualitatively significant for the explanation of all the following except the structure of the periodic table, specific heat of metals, the anomalous Zeeman effect, deflection of a moving electron by a uniform magnetic field, or the fine structure of the atomic spectra. So going through these, you can quickly eliminate all of the answers if you're not sure exactly which one. So going through, A is a quantum effect, C is a quantum effect, and E is a quantum effect. If you're not sure about the specific heat, that is also a quantum effect, but it leaves you with B and D. And if you know what causes the deflection of a moving electron by a magnetic field, a point charge in a magnetic field is due to the Lorentz force, which we have seen plenty here, and that is a classical effect which just relies on the charge of the electron, so that gives us an answer of D for that one. The next question. Eigenfunctions for a rigid dumbbell rotating about its center have a phi dependence of the form psi phi is a e to the I m phi, where m is the quantum number and a is a constant. Which of the following values of a will properly normalize the eigenfunction? So looking at that, we have to remember that in order to normalize psi of phi squared phi will equal 1, and that for this we have phi star phi, where phi is the complex conjugate, equals 1. So this is more of a plug and chug. So I have a e I m phi, minus, and then times a e I m phi d phi, that's equal to 1. Doing some mathemagic, I get a squared e to the minus I m phi plus I m phi d phi equals 1. Those are going to cancel out to 0. And sorry, this is going to be a to 2 pi, or 0 to 2 pi. I have a squared times, that'll just go to 1. So I'll have the integral of 0 to 2 pi of 1, so it would just be 2 pi equals 1. A is going to be 1 over root 2 pi, which is answer D again. All right, for the next problem, we have a negative test charge is moving near a long straight wire in which there is a current. A force will act on a test charge in a direction parallel to the direction of the current if the motion of the charge is in the direction blank. Okay, so I have a straight wire, boom, current is flowing along that wire in that direction. I have a test charge here. Force will act test charge. So this is essentially asking about the right-hand rule. So I have here is the current out of the page. and it looks like I have towards and away. So if I have a magnetic field here, boom, current there, then the charge based off the right-hand rule, these are together, this is out of the page. The right-hand rule was just going to tell us that it would be moving towards, but it is a, what does it say? Negative charge, so it'll be the opposite, so it will move away. You can also use the left-hand rule for a negative charge, which is just the inverse, which just has, there'd be the current, there'd be the B field, and there would be your particle movement. So that one is testing your knowledge of the right-hand rule. Now on to the next one. There we go. So configuration of the potassium atom is in its ground state is one is that list of numbers and symbols. Okay. Which of the following statements about potassium is true? The N equals 3 is completely filled. That is incorrect, because if you see, it only goes up to P, but it would need to go up to D to be filled, so that is wrong. For S, that is also wrong, because that number there would need to be a 2. Least tightly bound electron is L equals 4. That is incorrect based on this value here. This would be the 3, I believe. I know it's not at least 4. Atomic number is 16, or I'm sorry, 16, 17. I can read numbers. 2, 4, 10, 12, 18, 19. That is incorrect. Just based off, this kind of tells you how many electrons are in each thing. So just basically by process elimination, we can get to E. But let's give an answer of why it's E. So if I have my potassium, that's 4, 1, 2, 3. Ignore the awesomeness of these circles. There we go. This one is 2 is full. So let's basically, boom, expand that out. I just have a single electron in this fourth shell. So if we kind of just look at the outer one, it's very similar to a hydrogen with just that one, which is spherical in its symmetry. So boom, we have E as our answer.